In the last lecture, I defined a logic circuit as something that must have a set of inputs and outputs and a functional specification and a timing specification. The functional specification is equivalent to its behavior, and logic behavior can be defined in Boolean logic expressions. So for example, if you take a full adder circuit, which is a 1-bit adder that's used as a building block to build wider adders, it has 3 inputs A, B, and C in, and 2 outputs S and C out, all of which are 1 bit wide. And its behavior, or its functional specification, can be defined by 2 Boolean logic expressions that compute S, the S output, as a function of its all 3 inputs, and C out as a function of all 3 inputs. So for example, in this case, S is defined as A XOR B XOR C in. Before moving on, let's agree on the definition of some of the terminology. A complement is a logically inverted Boolean variable, which is shown in a number of ways depending on the source. In the textbook and in my lecture slides, I show a complement as a variable with a bar, a horizontal bar over top of it. But sometimes you'll see a tilde preceding a variable as a complement. In fact, System Verilog, the language that we'll cover soon, uses that representation. Sometimes you'll see a complement denoted as an L that's rotated 90 degrees counterclockwise and used as a prefix for a variable as a complement. Sometimes you'll see an accent that comes after the variable as denoting its complement. And sometimes you'll see a not function used, where you'll have not of A, for instance. And sometimes I actually use this notation when I write up my answer keys for my quizzes and exams, just because it's a little bit more convenient to represent it that way when you're typing. But regardless of how you represent it, if the value of A is true, its complement is false, and if the value of A is false, then its complement is true. In Boolean algebra, a product is analogous to joining variables with the AND operation, and a sum is analogous to joining variables with the OR operation. An implicate is a product of literals, and a minterm is similar to an implicate, but the difference is that a minterm includes a literal that corresponds to all of the input variables. So if my inputs are A, B, and C, a minterm must include a literal for A, B, and C, and they must be joined together with an AND, so they're a product. There is one minterm that can be used to represent each of the possible logic assignments of all the input variables. So if there's n input variables, there are 2 raised to the nth power possible input combinations, and thus that's also the number of minterms. This way, any input variable assigned to 0 has a corresponding literal in the minterm that's in the complemented form. And any input variable assigned to 1 has a literal that is in the non-complemented form. Minterms can be enumerated, meaning numbered, assigned a number, a numeric identifier, according to the binary value that's formed from the input variable value. This, of course, assumes that there's some ordering among the input variables. So if my inputs are A, B, and C, I might assume that A represents the most significant of those 3 bits, and C represents the least significant. So an assignment of 0, 1, 1 for A, B, and C would represent the minterm 3, right? So sometimes you'll see min terms just identified as numbers. Now the sum of products canonical form, sometimes abbreviated SOP canonical form, is when a Boolean expression is written as a sum of min terms. And to be clear, technically SOP form requires min terms as opposed to implicates. Although this can be a little confusing because sometimes you'll see expressions formed with implicates and it may be referred to as SOP form, but it's not SOP canonical form if in fact that is the case. So if you sum all the min terms that correspond to the input values that yield a true value, then you have the SOP form. Now here's where things get a little strange. There's also something called a max term. A max term is like a min term, except instead of a product, it is a sum. And again, a max term must contain a literal for all the input variables. However, max terms differ in one important way, and they follow the opposite rules to min terms when it comes to constructing a max term from an input value combination. So every variable that has a true value is actually complemented in the max term, and every variable that has a false value is non-complemented. Okay. So a product of sums canonical form is pretty much what you'd expect it to be. It is a product of max terms. However, when you build a product of sums representation, you're actually building it in the opposite way. You construct the max terms according to the values that produce a false value in the truth table. And you might say, well, how does that work? I mean, well, what's really happening is fundamentally you're building a sum of products for all of the 0 output rows in the truth table, right? But then you do De Morgan's law by negating the sum of products, which converts it into a product of sums and complements all of the individual literals that formed the original sum of products, that were part of the original min terms in the sum of products. Now you may say, well, why would you choose one form over the other, sum of products versus product of sums, when creating Boolean logic expressions to perform a Boolean behavior? Well, it's pretty simple. If there are more 1 outputs in for a function, then it would be more efficient, possibly, or at least require less gates, to use the product of sums. Whereas if there are more zeros in the output column of a truth table, then you would use sum of products, because that would require less gates. So let's look at an example. Say we want to derive a Boolean logic behavior that predicts if we'll eat lunch. Assume we decide that we won't eat lunch, meaning that our output variable e is 0 if the cafeteria isn't open, which means that the input variable o is 0, or if they only have corn dogs, meaning that the input variable c is 1, because let's just assume that I don't like corn dogs. The first and second row of this truth table has the way that the rows of the truth table are laid out. The first and second row have O equals 0, meaning the cafeteria isn't open, and the second and fourth row has C equals 1, meaning that the cafeteria is serving corn dogs. So as a result, the only value where the output value E is 1 is the third row. We can add the minterms to the table by complementing the literals with a corresponding 0 value, and we can add the max terms to the table by complementing the literals with the corresponding 1 value. We can derive an SOP expression by ORing the midterms for the rows with an output of 1, and the product of sum expression by ANDing the max terms on rows with an output of 0. Truth tables can also have multiple output columns. This example here shows a priority circuit which asserts one of its 4 output bits corresponding to the position of the leftmost 1 bit in its 4 inputs. This table has 4 inputs, so there are 16 rows in the table, but there's actually only 5 unique output combinations. The 5 being, the first being that there's no 1s in the input, the second being that the leftmost 1 is in position 0, all the way to the 5th output that corresponds to the leftmost 1 bit in the input being in the bit position 3. The third and fourth rows have the same output value, and they're the only rows where A3 to A1 are 0, 0, 1, meaning that these rows include or cover every possible value of input 0. So you can collapse those rows into a single row with input A0 being a don't care or X. Now, recall that we previously used the value of X to stand for contention, which was a bad thing. So don't cares are kind of a good thing, and contention is a bad thing, but we're using X for both. Unfortunately, this is also how it works in System Verilog, meaning that the X value has different meaning depending on if it's generated by the simulator, or if it's something that the user, the programmer, the designer has explicitly set in the code. Now in this table, likewise, the 5th and through 8th rows have the same output and are also the only rows where inputs A3 to A2 are all 0, 1, meaning that these rows cover every possible value for inputs A1 to A0, so we can then collapse these into one row with a don't care value for A1 and A0. Likewise, rows 9 through 16 are the only rows where the input value A3 is 1, meaning that we can list don't cares in those cases for A2 to A0. So next I'll talk about a very important digital logic building block, the multiplexer. Recall from the previous lecture that you cannot connect the outputs from more than one element to the same wire, because this creates contention. You can connect an output to multiple inputs, you just cannot connect 2 outputs together. In other words, you cannot have more than 2 logic elements attempting to drive or set the same net or wire in your design, or signal. Multiplexer kind of solves this problem by allowing 2 or more elements to effectively share the same wire by allowing a control signal that gives control of that wire to only one element at a time. So, in other words, multiplexers allow for the design of data paths, which are logic paths that can be dynamically established by a controller. It allows multiple logic elements to provide an input for one logic element by essentially time multiplexing a wire. So, for example, it allows a register file to accept an input from either an ALU or a RAM to support like an add instruction, in which case we need to send the value from the ALU to the register file, or a load word instruction, which is when we'd have to send the value from a RAM to the register file. A multiplexer has a set of inputs. The number of inputs is usually a power of 2, but it doesn't have to be. And any of the inputs can be logically connected to the multiplexer's output at any given time, depending on the value of the select input on the multiplexer. An n-input multiplexer requires a log base 2 n select input, where n is the number of inputs. So if there's 8 inputs, you require a select input that's 3 bits. Or if you have 2 inputs, you need a 1-bit select. A 2-input multiplexer has 3 total bits then, right? So there's 2 inputs and 1 select, which can be shown as an 8-entry truth table, 2 to the 3rd power. Like the priority decoder, when the select input is 0, the first input, D0, is forwarded to the output, while the second input, D1, is ignored, making it a don't care. Likewise, when the select input is 1, the second input, D1, is forwarded to the output, and the first input is a don't care. If we drill down into the multiplexer abstraction, we could potentially see different implementations. One way is a traditional SOP or POS implementation. Of course, we can also minimize that with Carnot maps, as you learned in CSCE 211. Note that we don't I'm not going to cover logic minimization in this course, but we assume that you're comfortable with it and that you remember it from CSCE 211. If not, or if you feel that you might have forgotten, it's in the textbook. It's described thoroughly in the textbook. It is also possible to build a multiplexer by allowing multiple inputs to directly connect to the output wire, which normally you can't do, but if you use tri-state gates, as we described in the last lecture, as long as only one of the tri-state gates is active at a time, you can basically use the select to determine which of the tri-state gates is active, and use that to turn on only one of them. So essentially, you've built a multiplexer using tri-state gates. However, if you have any more than 2 inputs, then it relies on a decoder to select which tri-state is active or turned on, and I'll get to decoders here in just a moment. In addition to providing a way for multiple signals to share a single wire, which is what we'll use multiplexers for most often in this course, multiplexers can also be used to implement logic, by hardwiring the inputs to the multiplexer to the values in the output column of a truth table, and then using the select input as the input for the function. So this way, you're basically just selecting which of the entries in the output column of a truth table you want to forward to the output. Another digital building block that's just as important as the multiplexer is the decoder. A decoder has n outputs, of which it sets one of them to 1 and the others to 0, based on the input bits. The inputs, there are log base 2n inputs. So if there's 8 outputs, there'd be 3 inputs. If there's 4 outputs, there'd be 2 inputs. And if there was 16 outputs, there'd be 4 inputs. The binary value of the inputs determines which of the outputs are set to 1. I often refer to decoders as a binary to unary converter, because you pass a binary value in and you get essentially a unary value out, which is a set of wires in which only one of them is active depending on the binary value passed to the input of the decoder. If we drill down into the abstraction of a decoder, there's multiple ways to implement it. One simple way is to use a single level of logic as opposed to a POS or SOP form that's 2 levels of logic, where each output is driven by just one AND gate, and each AND gate has the same number of inputs as the decoder, and is essentially each one of them is a unique minterm. So the first AND gate, the least significant, so the AND gate corresponding to the least significant output bit would be minterm 0, and the next one would be minterm 1, and so on. Like multiplexers, decoders can also be used to build arbitrary digital logic functions, since it essentially outputs a single bit corresponding to each minterm. So you have an input come in, you'll have a wire that will light up corresponding to the minterm that input represents, and then you can thus choose a subset of the output wires to feed into an AND gate and implement an arbitrary sum of products logic circuit. Now obviously this would be less efficient than building an actual SOP or POS implementation, but that's just something that it can be done with decoders. So that's all for our quick introduction of digital logic behavior. Hopefully most of this was a review from CSCE 211, and the next lecture will introduce hardware description language. A multiplexer has a set of inputs, each of which can be logically connected to a single output and multiplexer has a set of inputs